Hi there. Thanks for joining us again on Space Nuts Q&A edition. My name is Andrew Dunkley. Lovely to have your company. On this episode, we're going to be answering some audience questions from Mikey. He is asking a really interesting question. Can we drink water that is on the moon, as in moon water or lunar water? Would that be a good idea, even if we clean it? That's a good question. We'll see if we can come up with an answer for that. Sean is asking us about Nemesis theory, and Rusty has a question about the Hubble constant. That's all coming up on this Q&A edition of Space Nuts.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2.
1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
And he's back again to help us out with all of that. Fred Watson, astronomer at large. Hello, Fred.
Hello, Andrew. Fancy seeing you here.
Indeed. It's like you never left, really.
Well, I did, obviously, because I've got a coffee now.
Yes, you have. Yes. All right. Now, we do have a few interesting questions to deal with, and we might get straight into it. Our first question today comes from Mikey.
Hey, Fred and Andrew. Mikey from Illinois with a quick question. So eventually when we get to the moon and Mars and start using the water available to us there for things such as drinking, should we drink that water? I mean, I know that we'll use whatever ways and processes we know how of now to clean that water and purify it like we do on Earth, but are there chances that there will be stuff in that water that we might not even know exists yet, that we might not have ever seen before, that could have detrimental effects to the human body? It makes sense to me that you would drink the water that's available to you after purifying it, but it also just raises concern in my brain that maybe something will be in that water that we don't yet know. Would you guys drink the water after being purified the first time, the 10th time? Curious what you guys have to say about that. Thanks.
Thank you, Mikey. Well, I've drunk some pretty horrible stuff in my life, probably worse than water from the moon, so I probably would. It's an interesting question, though, Fred, because is it possible there's something in the water that we don't know about? There are things on the moon that aren't readily available on Earth, so could it be something in the water?
And it's a good question, and thanks, Mike, for asking it, because it goes to the heart of something we talked about before as well. But yeah, I mean, I guess taking the question at face value, what if there's something that's not known to science that is in the water that could be harmful, and that we with all our checking and testing of the water samples, basically people saying, okay, that's fit to drink, and yet there's something in it, particularly perhaps with Martian water, maybe some sort of Martian microbe that we haven't got any way of detecting. I'd still drink it, actually.
Oh, there you are. So
yeah, that's. I think I would, and that's because I'm a scientist. My colleagues would have tested it to death, and so if there was something in it that we didn't know about and it had an effect on me, so if I grew antlers all of a sudden or something, it would be a big scientific discovery, and I would have been part of it.
Right.
Fred Watson with antlers. But there is something a bit more perhaps realistic and that will clearly have to be dealt with that we can discuss. And we've discussed it before, because the water on the moon and on Mars will probably not have the same isotope ratio as the water on Earth. It will have a different fraction of heavy water in it from the water that we have on Earth.
Oh, okay.
And there'll be a different ratio between normal water and heavy water. Remember, heavy water's, it's sometimes called D2O rather than H2O because the D is deuterium, which is hydrogen in a heavier form. It's called heavy hydrogen. With an added neutron. So,
and we're not talking about the heavy water from a nuclear reactor. Let's get that clear. This is natural heavy water.
Yes, it is. That's correct. That's right. And we've done measurements of comets, which are made of ice, and discovered that the proportions of heavy water to normal water are different from what they are on Earth. And so that's something that does make the water different in a comet, and it's likely that the water on the Moon and Mars perhaps came from comets, so it may well have a different isotope ratio, so a different basically quantity of proportion of heavy water to normal water. Now,
a different balance.
Indeed, that's correct. A different balance, yeah. Which we talked about at length in a previous episode of Space Nuts.
Yeah.
The question is, can you drink heavy water? The answer is you can. If you have smaller amounts, it won't affect you. But if you drink too much of it, you'll start getting a different effect because it's more dense. That's why it's called heavy water. It's more dense than normal water. Excuse me. So, if you've got differences in the density of the liquid that's going around in your body, and in particular, I think perhaps the really sensitive region is the fluids in your ears. If they suddenly start getting heavier, you might start getting nausea and things of that sort because your balance is affected by heavy water. But if you drink too much of it, then you've got this higher density running through your body, and it would be very toxic. It would probably be fatal if you drank, pure heavy water for a long period. I don't think you'd be very well.
No, we have touched on that before, and it's it's an interesting problem that they face. I was doing a bit of research on this particular question because it fascinated me so much. There was an article in space.com in January this year, and two of the major space agencies have said, look, we're going to be using the water on the moon ultimately, but we need to filter it. And they've called for public assistance on a project called Lunar.
Okay.
And they want people's ideas on how to filter the water on the moon. So it could be consumable. So they are actually thinking about drinking the water on the moon.
Yeah.
They might have to do a bit more homework, but they've opened this competition up to people in Canada and the United Kingdom. Now, I think the deadline was April the 8th. So it'll be interesting to see what comes out of that. But they're certainly looking pretty seriously at making that resource available for consumption.
But if you do have a significant ratio of heavy water to normal water, no matter how much you filter it, you're not going to get rid of that.
No.
And so it's an interesting question. Should you be drinking it if there's a large amount of it?
Indeed. Yeah.
So, I, as I said at the beginning, I probably would have a go. But
I wouldn't mind. I mean, one glass of slightly heavily laden water wouldn't kill you, but if it's all you had to live on for a long period of time, probably would. It'd take a while.
That's right. Probably would. It's the figure I've read here. If you have the amount of heavy water in your body, if it reaches 20% of the total water in your body, it could be lethal. So you've got to watch out. Yeah,
indeed. All right, great question, Mikey. Thanks for sending it in. Our next question comes from Sean.
My name's Sean. I'm from Nottingham in England, and I heard about Nemesis theory and that there might be a small sun in our solar system somewhere. And I wondered whether there was any possibility of this and whether this could be Planet 9 if it's like a small neutron star or something. Okay, look forward to hearing your answer. Bye.
Thank you, Sean. Nemesis theory first postulated, I love that word, in 1984. And they're talking about the potential for a small sun around 95,000 AU from our main sun beyond the Oort cloud is where they're thinking it might be. So is that possible, Fred? Could that be Planet 9, or could it be something else, or could it just be a complete myth?
So so you've got to look at why that was hypothesized. You're absolutely right, Andrew. It's something that was proposed by astronomers back in the 80s, and it's sort of it's not been disproved. Actually, it's still it's in the background of what we do in the world of astronomy. Is there an object which would have been originally the sun's binary companion, and it still is, in the sense that the hypothesis is that this object is in orbit around the sun, or is the two objects are in orbit around a common center of gravity. As distinct from, I'm just going to say this briefly, that there are other theories of things like this, and perhaps the best known one is Nibiru. Nibiru is the supposedly a hostile star that's going to consume the Earth, and we can't see it because it's on the other side of the sun. Nibiru
I think Nibiru's got its own cult.
It's complete rubbish, absolute rubbish.
Yeah.
And in fact, I can quote Brian Cox. He didn't say this to me, but I heard it said, "If anybody else mentions the bullshit planet Nibiru, I'm going to throw a copy of Newton's Principia at their head."
That's right. I remember that.
Yeah, that's right. So, Brian summarised it in perhaps a more forthright way than I would, but yeah, it's rubbish. Nemesis, however, isn't. Nemesis is different, and it's thought to be, the hypothesis is that there is the sun's binary companion, the companion star that the sun was born with, because we know that most stars are born in pairs. Which we've never found. We've never been able to identify that companion of the sun. And the hypothesis is that it is out there lurking, as you said, 1.5 times, what was it, 1.5 light years or something of that sort away from our own planet. 95,000 astronomical units, the distance between the Earth and the sun. So why do people postulate it? Is it just that we do think that the sun has a lost companion, a lost sibling somewhere? Yes, that's partly it, but there is more to it. And this is really the reason why this was hypothesized. And it actually goes back to some work that colleagues of mine were involved with around the same time, in fact, before the Nemesis hypothesis in about 1979. The idea, and this seems to be supported by the geological record, that on a timescale of 26 or 27 million years, you get repeated mass extinctions. So you've got this periodicity in mass extinctions, if I can put it that way. So the geological record, the fossil record, as you dig down through the Earth's crust and you look at the different layers, geological layers, every 26 million years or thereabouts, you find that species are being made extinct. They disappear.
Yeah.
And the suggestion is that possibly this is to do with the orbit of Nemesis. If it comes closer at one part of its orbit than another, then it will have tidal disruption of the Oort cloud. The Oort cloud will then bombard stuff into the inner solar system, and you get mass extinctions. It was my two colleagues, Victor Klug and Bill Napier, in 1979 who first suggested that. They wrote a book called The Cosmic Serpent. They were a bit more specific about some of the comets that were involved, but that was the general theme. But they didn't postulate there being another star doing this. they postulated that as the sun goes round in its orbit around the galactic center, it periodically passes what we call giant molecular clouds, which are stellar birthplaces. And in doing that, it feels gravitational or tidal disruption from those objects, and you get the same effect. You get stuff being dropped in from the Oort cloud into the inner solar system and potentially mass extinctions. So that's a rather different theory. But both those theories are still lurking in the background. The search for Planet 9 is much more local. We're looking for an object that's much nearer, measured in hundreds of astronomical units rather than tens of thousands, which you'd have to be if you had a periodicity of 26 million years or so. You've got to be looking at something a long, long way from the sun. So Planet 9 is nearer objects, a nearer object if it exists, which is perturbing the orbits of trans-Neptunian asteroids, things like the Kuiper belt objects and other icy worlds out there. So I think Nemesis falls into the same basket almost as Planet 9. We've got this, what you might call circumstantial evidence that there's something going on there, and there is a theory that sort of kind of goes some way towards explaining that, and that's the case with Planet 9 and the trans-Neptunian objects, with Nemesis and the mass extinctions. A lot more research, I think, has been done on both of them than we're discussing here. Various ideas have been eliminated. It's instructive to go, as I'm sure you have, Andrew, to the Wikipedia page on Nemesis. It's very instructive. Let me summarize by reading what the last sentence in the Wikipedia entry on Nemesis is, which reads, according to a 2011 NASA news release, recent scientific analysis no longer supports the idea that extinctions on Earth happen at regular repeating intervals, and thus the Nemesis hypothesis is no longer needed. So, it brings geology and astronomy together, but it looks as though the geology no longer supports it. We know much more now about the geological record than we did in 1984. So maybe Nemesis is out of the window.
Yeah, well, it certainly sounds like it has absolutely nothing to do with Planet 9 theory. And even if Nemesis does exist, it's probably too far off to have any real effect, by the sound of it.
Until it comes close enough to disturb the Oort cloud and we suddenly get bombarded by comets.
Yeah, good point.
Which is the point that they're making in this.
Yeah, so, hence the name Nemesis, I suppose.
Indeed. Yeah. In actual fact, there's a coincidence here because one of my colleagues who were mentioned at the Royal Observatory in Edinburgh, Victor Klug and Bill Napier. Victor was my boss, actually, working on different sorts of stars. But Bill went on, he now lives in Northern Ireland. He wrote a book called Nemesis. It was a science fiction novel. Nemesis.
I've read it.
You've probably read it. It's actually in my bookcase just over there.
Yeah.
But it was about an asteroid rather than a star.
Yeah, and it was how they stopped it hitting Earth.
Which
was an actual workable possibility. It's one of the theories they've been working with to deflect or divert an asteroid away from Earth should it be a threat. It's a really good book. I read it some time ago and I really enjoyed it. Great idea. And thanks for bringing up the question, Sean. Nemesis, probably not Planet 9, but it's certainly something that's got a lot of people speculating. This is Space Nuts. Andrew Dunkley here with Professor Fred Watson.
Okay, we checked all 4 systems and keying with a go.
Space Nuts.
Next up, and our final question today comes from Rusty.
Fred and Andrew, it's Rusty in Donnybrook. Just been listening to your episode 407, and I just want to ask a question regarding the Hubble constant. The CMB method yields 67 kilometers per second per megaparsec, and the standard candle method yields 73 kilometers per second per megaparsec. Is it possible
that the interstellar medium is causing the standard candles to lose some intensity over the distance. In other words, some of the light being absorbed by the interstellar medium. If that was the case, then it would appear that the CMB method, yielding 67 kilometres per second, might be closer to the mark. Is that possible?
Thank you, Rusty. Rusty, always insightful, but again, as I mentioned earlier, has an idea. So we should discuss that. But the Hubble constant, we did speak about recently because of that ongoing differential in the expansion rate of the universe that they can't figure out.
Yeah, the Hubble tension, it's called.
But Fred's figured it out. What's the answer?
No, I haven't. Sadly, I don't think Rusty has either. Well, which I'll come to in a minute. But just let me explain what the gobbledygook words are that Rusty used. He knows, Rusty's well across all this, so these gobbledygook terms that we use are familiar to him, but not to everybody. So those figures measured in kilometers per second per kiloparsec, per megaparsec, I beg your pardon, kilometers per second per megaparsec. Just giving a blanket understanding of what that is, it's how fast the universe is expanding now. It's expansion speed. The further out in space you look, the more rapidly things are moving away from you. And that's all that does. It puts it into numbers. But as Rusty says, we get two different estimates. 67 comes from the cosmic microwave background radiation, what Rusty correctly describes as the CMB. And that's caused by looking at the patterns in the cosmic microwave background radiation. We mentioned that in a recent episode of the Space Nuts chat, that there is a pattern of slightly higher and lower temperatures in the cosmic microwave background radiation, and that pattern gives you a value for the Hubble constant. And exactly as Rusty says, when you look at standard candles, and in this case these are supernova explosions at great distances usually, then you get a different answer. You get 73 kilometers per second per megaparsec. Now, Rusty's thinking is right on the money, but astronomers think the same way. And so they will be looking for any evidence of some influence of the interstellar medium on the measurements that we make of supernovae. There's an analog that perhaps I can point to here. When we measure the brightness of stars in space, normally, if you know what type of star it is, you know how intrinsically bright it is, and if you measure its apparent brightness from the Earth, that's a measure of how far away it is, because you know it's a standard candle. You know how intrinsically bright it is. If you measure its brightness from Earth, what we call the apparent magnitude, then it's a very easy calculation to work out how far away it is. But there may be intervening material, and in fact there nearly always is, because space is pretty dusty. It's got dust in it. Yeah. And the dust tends to dim the light from the star, and so that means it looks as though it's further away than it actually is. Now, is that the right way around? Yes, it's dimmer. It's dimmer, so you think it's further away. Just got to think about this. Sometimes these things work not the way you want them to. So, so how can we tell if there's dust there? Well, it turns out that dust does something to light, and we think of it as smoke, but it's more like smoke, but we call it dust. What it does is it scatters out the blue light, just like the atmosphere is scattering blue light. And so a star's light, if it's passing through dust, will be reddened. And you can measure how much that reddening is because you know what type of star it is, so you know what its colour is. And if the colour is moved to the red, you can say, there is dust there, something we call the colour index. And that lets you correct the distance that you're looking at. So you can correct the standard candle because you know that what's happened is the dust in space has kind of put a signature on the light coming from the star, which tells you that it's not just empty space in between. And similarly, the light from supernovae will have printed on them a signature of the interstellar medium. And that's something that some of those signatures are mysteries, actually. In interstellar space, for a long time, there's been a signature in space that we really didn't know what it was, but it turns out that it's things like buckyballs. It's complex carbon molecules that absorb light in a particular way. So what I'm saying is that because the light from these distant standard candles has been analysed to death, any impact by the interstellar medium will have been compensated for because it will have left a fingerprint on the light or a signature on the light, which we can detect. So I think the answer to Rusty's question is, A, I like your thinking because you're thinking along exactly the same lines that astronomers think, and B, I think the odds are that we would have known had it been some effect of the intergalactic medium, the space between stars, that would be causing that phenomenon. And there is a standard ruler method as well that just looks at the distance, the difference in the characteristic size of galactic clusters and things of that sort, which also gives that 73 kilometers per second per megaparsec. So it's not just the standard candles. But thank you, Rusty. A very stimulating question as always.
Yes, back to the whiteboard and get a new packet of Sharpies because you've still got some calculating to do. But yes, not the solution, but I'm glad someone's thinking about it. I think a lot of people are. But no solution to the variations in the Hubble constant. Thanks, Rusty. Remember last week, Fred, we answered a question from Craig, who identified himself as a science fiction writer, and I said, "Tell me what your books are, and I'll have a look at them." Well, he sent me a copy of his book. It's called Freya's Flight, and it's his tribute to Heinlein's Juvenile series. So I'm going to read that and let you know what I think in about 2 or 3 years' time, because I'm a slow reader. But he also sent me his Amazon page for Freya's Flight, Kindle edition by Craig Miller, if you want to look it up and have a read of Craig's book, who sent us a question last week. He said he was funny because it took me a while to get that one into the system. He said, I thought my question had fallen off your desk. Well, it virtually did, Craig, because it actually fell off my computer because I did a computer update and it wiped everything. And it took me ages to find all the stuff. But it turns out there was a corruption in my Microsoft OneDrive cloud software, which was confusing my account with another account that I had at work, and they got jumbled, which has happened to me a couple of times. So, and then it was trying to find a drive that didn't exist on my computer, and dogs and cats ended up living together. It was all over Red Rover. But thanks for a copy of the book, Craig. I'm looking forward to reading that. And look for Freya's Flight if you want to read Craig's book as well. That brings us to the end. Fred, thank you so much. We'll catch you next time.
It sounds great, Andrew, and it'll be as exciting as it was this time, I'm sure.
Maybe more so. Who knows?
Oh, I can't take much more excitement, I have to tell you.
No, not at all. Definitely not. All right. See you soon, Fred.
Cheers.
Fred Watson, astronomer at large. And thanks to Hugh in the studio for what I will tell you next week. And from me, Andrew Dunkley, thanks for your company. And we'll look forward to joining you again on the next episode of Space Nuts. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at bytes.com.
This has been another quality podcast production from bytes.com.